Catalan, and this is my presentation. The purpose of this experiment, for part 1, it's to determine the estimation of the mass of the black hole based on the star's motion around the black hole. For part 2, it's to determine the initial velocity of the ship must go around a black hole, not necessarily in orbit, to just go past it without actually hitting it, based on the mass of the black hole that we calculated from part 1. A brief preview is that part 1, the average mass of the black hole is 9.27398 times 10 to the 33 kilograms. For part 2, the initial velocity is -4 times 10 to the 7th, 2 times 10 to the 6th, and 0 meters per second. Physical principles, we have Newton's second law, which essentially just relates the interaction of the system and surroundings with the observed motion of the system, which is just a change in momentum, and this momentum is just how easy or difficult it is to change in motion. The motion of an object. Gravitational force is just the force of attraction between all masses in the universe. In our specific case, the force is non-constant, which means that the average velocity is approximately equal to the final velocity, which we end up using for the position update formula. Here you have calculation for Newton's second force. Through manipulation, you can get the momentum update formula and velocity update formula, and the position update formula is just given at the bottom, and what we discussed before in a scene. Gravitational force, the equation is given here. G is a gravitational constant, minus r hat is the direction of the force towards the source. Mass 1 and mass 2 is m1, m2, and then r in general is just the position vector between the two masses. For net force components, the composite forms is the parallel and perpendicular component. As you can see, it can be calculated through manipulation on the right, and it's used for part 1. Initial conditions for part 1, the system is a star because we're using the star's motion to actually calculate the net force, or to get net forces to calculate the mass of the black hole. Surroundings is the black hole and everything else in the universe. The mass of the star is 2 times 10 to the 30th kilograms. Delta T is 1 day in seconds, 86,400 seconds, and then the initial time is 0 seconds. Here, the only thing is that the seed is created through my Georgia Tech HEMO. The mass of the star is given in line 122, and delta T is calculated in 125. And here, line 166, we are just calculating the initial and final momentum based on mv. V would be changing depending on whether it's initial or final. 170 and 171, we are just getting the differences in velocity and the difference in momentum. For 174, we are dividing the delta P over delta T, and this is equal to F net. We can calculate P hat by getting the unit vector or the direction vector of the initial momentum, and we can calculate dmag pdt, which is just the magnitude of the final velocity, final momentum minus the magnitude of the initial momentum divided by delta t, multiplying this by p hat is equal to the parallel net force component, and subtracting this by the net force gets the perpendicular component of net force. Here r is the magnitude of the position between the star and the black hole, and we can calculate the mass of the black hole just by basically rearranging the force of gravity. As you can see, the mass of the black hole total is being added to see the total mass of the black hole, and then there's a counter, so you can divide it by actually get the average mass of the black hole, and then everything else underneath is just the arrow scales and how it will be seen. Here is the code. I'll just show a very small snippet of it. As you can see, it changes. Here are the results. FNAT is 7.7789 times 10 to the 28th. The parallel component is 3.39153 times 10 to the 27th. The perpendicular component is 7.76962 times 10 to the 28th, and is calculated to be the average mass of the black hole is 9.27398 times 10 to the 33, which is actually what we use for the initial condition here. The system is the ship. The surrounding is everything else. The black hole, the planet. The mass of the planet is given as 9.10 times 10 to the kilograms. The mass of the ship is given as 7 times 10 to the 10 kilograms. Delta T is 1 second, and initial time is 0 seconds. The ship's initial velocity is found to be -4 times 10 to the 7th, 2 times 10 to the 6th, and 0 meters per second. Here's the code. Line 31 is just the initial conditions. We use the guess and check method for line 61 and 62 to actually find the velocity. Here, for line 79, we find the distance between the planet and the black hole, and then we just essentially use this and other values to with the force of gravity equation to get the force from the black hole on the planet, and we do the exact same thing, but for the ship and planet, we add these two forces together to get the net force on the planet, and we do the exact same thing, but for the black hole and the ship, and the planet on the ship, add these two net forces together, or these forces together, to get the net force on the ship, and we use the velocity update formula and position update formula later on in the bottom for both the planet and the ship. Here's the results. Sources of error. The average mass of the black hole calculated in part 1. If you have a higher maximum time, this means the while loop will go on longer. You have more calculations, which means that you can get a more accurate average mass of the black hole. For part 2, the initial velocity of the ship is used through a guess and check method. If you use more decimal points, the trajectory would change, which would change the velocity through iterations of position. Um, Questions for part one. Mathematically, the net force and dp/dt are identical, but physically, net force is easy to observe but difficult to measure. The direction is observable, but the magnitude is difficult to determine. And for the change of momentum, it's easily observed and measured, just because it's mass and velocity. For part two, in theory, you can find it if the x and y components of the velocity are within 2 magnitudes of each other, but I personally could not find it.